Now we're going to talk about asymptotic normality and the central limit theorem. So here's something that's interesting. We saw actually earlier that even if our data, the measurement of interest itself, has some weird distribution, like this beta distribution, which is highly bimodal, when we estimate the mean of, say, 100 samples from that distribution, the sample mean itself, the distribution of that looked kind of like a bell curve. So here I'm showing you that same phenomenon. So I've done this already in R. What I'm doing is I'm taking for each value of n. So let's start with this one. N equals 2. So I'm taking 2 random draws from this beta distribution, and I'm calculating the sample mean of those 2 numbers, and then I'm recording it. And I'm doing that again, and again, so like 1,000 times. And then what I'm showing here is what value I got for the sample mean, how often I got it. So when my sample size is only 2, showing me like most of the time I'm getting a sample mean of 0.5. Sometimes I get a sample mean of 1. Sometimes I get a sample mean of 0. So the reason that makes sense is because this variable, let's go all the way back. This beta distribution, like I showed you, is very highly bimodal, right? So what's happening is basically I'm either getting, when there's a sample size of 2, these are the possibilities. I either get one number that's near 0 and one number that's near 1, in which case my sample mean will be about 0.5, or I'm getting 2 numbers that are near 0, or I'm getting 2 numbers that are near 1, because basically the number that I'm getting is either a 0 or 1, or close to 0 or close to 1. So those are the only 3 possibilities when my sample size is 2, which is why I get my sample mean. It looks like this. And in fact, the reason that this peak is higher is because there's 2 ways to get a 0 and a 1. I either get a 0 and 1, or I get a 1 and a 0. Whereas if I get a 0 and a 0 and a 1 and a 1, there's only one way. So I get like two times higher probability to get a 0.5 mean than a 1 or a 0. So I have this weird sampling distribution of the sample mean when I'm only drawing 2 samples. But as I increase the number of samples that I'm drawing from this distribution to generate the kind of like population of data sets that I'm averaging over to get this the sampling distribution, or not averaging over, but counting over to get this sampling distribution of the estimate, the sampling distribution of the sample mean starts to look more and more like this bell curve. So already when I'm sampling just 20 values for x here, the sample mean of those 20 values is looking very much like a normal distribution centered at 0.5. And here's another example. This thing is something much more complicated. So here, this is a sample mean, which is a very kind of simple estimator. Just take a sample average. Here's something much more complicated, where I have a much more complicated data generating process, where I have 3 random variables, which you can think of as like, some baseline covariate and some exposure, and then an outcome given that exposure and the baseline covariate. Here S is the logistic function. And my estimator is a more complicated thing. I'm looking at the group. This is the risk ratio estimator that we were talking about, the plugin before. Here I'm grouping by W. I'm taking the average in the 2 groups, and I'm dividing those 2 averages in the 2 groups. So this is what I'm doing each time, and I'm repeating this experiment 1,000 times. So if I do this experiment with sample size of equal to 2, and I repeat that 1,000 times, this is the sampling distribution I get. And again, this kind of makes sense because I'm dividing a sample average by another sample average. Y is binary, W is binary. So it's like either my average is going to be, both of these numbers are either going to be 1, 0, or 1/2, right? So when they're both 1/2, I get the risk ratio is 1. And I can get values of infinity or values of 0. And so I have this weird looking sampling distribution. When n equals 8, it starts to smooth out a bit. N equals 20, 53, 85, 150. Already it's starting to look very, very normal. It's not quite. I mean, it still seems like maybe it's a little skewed. But it's looking very, very close to normal, and it's seeming to concentrate maybe around somewhere near 2 as the mean. So That's very interesting. I've just shown you two examples, but it turns out this is a super common phenomenon for many, many, many estimators. You take data, you increase the sample size, the sampling distribution of that estimator as of whatever estimator you have as the sample size of the data that's going into it increases. That estimator, the sampling distribution starts to look more and more normal. It's a super, super common phenomenon. There's a reason for it, which we'll talk about in a minute. But first off, why is that useful? Why do we care that that's the case? And the reason is that if the sampling distribution of the estimator has a normal distribution, then we don't really need to fully characterize the distribution. We can just say, well, what's the mean and what's the variance? Because just with those two numbers, we know everything about the normal distribution. And in particular, since we're talking about the sampling distribution of an estimator, the mean relative to whatever the true value is tells us the bias, and the variance, the square root of that, the standard error, kind of tells us how random, how variable that estimate will be if we were to repeat the experiment. It's some measure of uncertainty. We'll formalize that a little bit more next week. So that's all we need to know. Okay, so why is it that this happens? So it's useful, okay? It's useful because it boils down everything about the sampling distribution to just two numbers. Then we ask, well, why is it that happens? It's really weird that even something as complicated as this still starts to look normal. This is another example where it doesn't even matter how the data are distributed. The sample mean starts to look normal. So it kind of happens a lot, and it's all tied to this thing called the central limit theorem. So the central limit theorem basically establishes that this has to happen for sample means. So if you take the sample mean of IID observations, independent and identically distributed observations, the sample mean of those, as n gets big, starts to look a lot like a normal distribution. That's just for sample means, though. So that's just one estimator, right? Why does it happen for this risk ratio estimator? Why does it happen for other kinds of estimators that we haven't even talked about? Well, there are other theoretical kind of like add-ons that start from the central limit theorem and extend it to other cases. Like, for example, the risk ratio, you can express it as this isn't exactly the risk ratio, but this is a ratio of two sample means. And it turns out that the risk ratio you can express as the ratio of actually several sample means. And when you have the delta method is something that says when you have a function of several sample means, you can kind of you can derive that the sampling distribution of that thing for large n is going to be also a normal. So it kind of comes from the central limit theorem and extends it. So then there's other results that have to deal with these things called M estimators. Like, for example, if you have an estimator where I'm not actually writing down explicitly the formula, like psi hat equals, this is what you do with the data. I define it implicitly, like this. So I say, for example, find the value psi hat, where if I take the difference between psi hat and each of my data points, and I add up all those absolute distances, I want that to be the smallest. So find me psi hat that minimizes this. It turns out that that's actually the sample median. But for any estimator that you can kind of write as some kind of minimization or maximization problem, it turns out there's a lot of theory that shows that a lot of those are normally distributed in the limit as n gets big. So it's crazy. But all of these results kind of flow from the central limit theorem. That's what I'm trying to show you here. You don't need to know how to apply these. This is definitely beyond your pay grade. I'm just trying to explain why such even complicated estimators, it turns out, have this kind of limiting behavior and can be described in large samples. Their sampling distribution is a normal. So let's zoom back in on this central limit theorem result and try to understand that a little bit better. The basic result is this. Any sample mean, so by any I mean doesn't matter what the distribution of z is roughly, is asymptotically normal, and the mean of that normal distribution will be the expected value of z, and the variance of that distribution will be the variance of z divided by n. Or sorry, so that's the variance, and the standard error will be the square root of that. So if we just know the expected value of z, this tells us about what the basically like the bias of our estimator will be, because we just compare that to what we're trying to estimate, which in this case is the expected value of z. If we're using a sample mean, we're usually trying to estimate a population mean. So what this says is that sample means are unbiased for population means, at least in large samples, and that the standard error of our estimator is related to, well, how many data points we're using and how variable this measurement is in our population. So that's nice. And indeed, this always holds. Basically always. There are actually some conditions, but they're quite technical, and you don't really have to worry about them in practice. But effectively, you can think up all sorts of crazy distributions here, and this will be the case. So here's the example that I was showing you earlier. Here, z has this beta distribution, so this is the density of it. It's very likely to be near 0, very likely to be near 1. And we saw that the sample mean of this, as we increase the number of samples of, say 20 samples, each of which has this distribution, will start to be normal. So, I mean, I've told you kind of that there exist these results, central limit theorem, delta method, whatever, that tell you why this should be the case. Understanding the mathematics of this result, it's actually pretty deep and not totally trivial. But I will tell you that there are some nice resources that you can access that will at least start to give you a general picture for why this should be the case, and what's so special about this normal distribution. Why is it that this particular density function that has like an e to the minus 1/2 x squared, right, scaled by some factor, why is that the thing that if you add up a whole bunch of other, because what are we doing here? We're adding up numbers. If we add up a bunch of random numbers, why is the distribution of the sum of those random numbers scaled always a normal, no matter what the distribution of these things is? And it has to do with this, how you get the density of a sum. So if you have two random variables, x and y, if I tell you x and y have the density fxy, and you imagine, the population data set x, y for each person in my data set. Let's make the like a scatter plot. Let's say the scatter plot looks kind of like this. So here's x and y, and again, this is like my drawing, like top down of like the density. You can also think of it as a scatter plot. Like there's a bunch of people near here, and then there's some sparser population outside of that. So if this is the joint density of x and y, the question is, let's say I have this population data set, and I do a mutate here to get z. Z is equal to x plus y. Okay, so I've done a mutate to get a new column z. And now I ask, if I plot the density of z, what will that look like? So if I know the joint distribution of x and y, how can I get the distribution of z? Again, if you have the population data set, you can like literally do this. You can just make the histogram, you can do this mutate and look at it. But mathematically, how is it that I go from the joint density of x and y to get to this this other variable? And in particular, what we're doing with the sample mean, like 1 over n of xi, right? That's very similar to this, because we're just doing x1 plus x2 plus x3 ... all over n. And in fact, the distribution of all these x's, so for any two of them, x1 and x2, they have the same, they're independent, and they have the same distribution. So my distributions will kind of look like this. They're not going to be, you won't have this kind of situation because there's no correlation, there's no covariance, right? If I increase x1, that doesn't tell me anything about x2 because they're independent, and they have the same shape. So if I look at this, like the marginal from one side, maybe it'll look like this. And if I look at the marginal from the other side, it should be the same shape because they have the same distribution. The x1 is equal to this marginal density of x2. So anyways, when you have this situation, how do you get what this density is. And that's something that you have to do something called a convolution, and it's not that crazy. Basically, you're adding up the values. So basically, if let's say z equals 0, right? If z equals 0 and we're having x and y, that means x has to equal y, right? And so if we're looking at this picture here, the line of x equals y is this line here, right? And so to get the probability that z equals 0, we have to add up all the probabilities along this line. To get if we want z equals 1, that means that x plus y equals 1. So the line that corresponds to that, like we can just do it like we had in like algebra class. Y is equal to 1 minus x, right? So, oh, sorry. For y 0, it's a y equal x. It should look like this. Sorry. It was this line. For z equals 0, for z equals 1, it's 1 minus x, so it's this line, and so on and so forth. So to get this value, it's adding up all the probabilities on this line. To get this value, it's adding up all the probabilities on this line. To get this value, it's adding up all the probabilities on this line. So that's what we have to do. And by repeating that process again and again and again and again, we end up, it turns out, getting normal distributions almost no matter what we start with. So these videos are fantastic. I really do highly recommend them. They take some time to go through, you can see. And I mean, they're not going to like help you in the course. It's really just, there's beautiful visualizations. This guy's a really great teacher, 3 Blue, 1 Brown. I recommend his stuff in general. But it will also hopefully give you a nice intuition about density functions, conditioning, marginalizing, things like that. If those are still kind of like things that are tricky for you, this will hopefully help you think about those topics as well, besides help you understand a little bit more about the central limit theorem. So anyways, I think it's fun. Have a look at them if you like. The link is also in the slides down here. This is the link to that whole playlist, so you can find that here, or just Google. Okay, so here the idea is just to replicate what I already showed you. So create a data generating process for any random variable z, and then use sampling with increasing n to show that the sample mean of z appears to be asymptotically normal, and then plot the sampling variance versus n. So what we have to do is what we did in the previous questions, where we're trying to generate a sampling distribution. The steps are: 1, set up the data generating process; 2, set up the estimator; and then 3, repeat that, right? So run over generating data, estimating the value, and then loop that and get a table. So you have like experiment 1, estimate 1, experiment 2, estimate 2, so on and so forth. And that gives you the sampling distribution. So that's what we're going to do here. We'll start with that. So it says use any DGP you want. So what the heck? Let's do this one. So we got one here already. And let's start with n equals 20. And let's set up, it says we want the sample mean. So our estimator as a function of the data. And all we're going to do is take the mean of, let's say, y, the variable y. So we're trying to estimate the mean value of y in the population. And y has some complicated distribution, okay, because it's depending on x and w, and who knows what all is going on here. So this is what we're trying to do. Okay, so we can show one run of the experiment. We generate our data, and we, sorry about that. So in one run of the experiment, we generate our data, and then we apply the estimator, which in this case is the sample mean, okay? Now what we need to do to generate the sampling distribution is repeat that a lot of times, which we can do with the map function. So let's say 1,000 times I want to repeat this. And I want to save the result not as a list, but as a vector of values. So let's do it like that. And let's save that as sampling dist. Or let's call it estimates. A little clearer. Okay. Let's have a look. Cool. And let's look at the distribution, see if it looks asymptotically normal, or if it looks normal or not. So we can plot here we go. Let's put more, see if this works. Yeah. So it looks pretty normal already, and n is only 20. Okay, so if I change n, let's move n down here so it's easier to see. If I change n from 20, this is 20, right? If I change it to 100 or 1,000, we're still in good shape here. And maybe it's even clearer if I just do the t. So this function here is r is function r that looks at that takes the histogram and then just kind of smooths it out a little bit. So you get a curve and don't have to manually specify like the different breaks. So let's see if that plots. Oh, right, because I saved it. There we go. Maybe it doesn't. How do you plot? Let's just use ggplot. Google it, but so for ggplot, I need it to be in a data frame. So I'm just going to put it in a data frame, and then let's sorry. What's going on here? Okay, that's working. There we go. Okay, cool. So yeah, here we go. Here's our approximate normal sampling distribution. And why don't we try it with a very tiny n? So like 3. See what that looks like. See, not so normal when n equals 3, not so normal when n equals 5. But as I increase this, it's going to get more and more normal. And already for n equals 10, it's looking pretty good. Okay, so now instead of looking at the sampling distribution, let's get an idea of what the sampling variance is for any n. So let's so if I have estimates, actually let's just take that right into variance. Okay, so let's start with n equals 5. Let's just have it print out. Okay, so for n equals 5, the variance is, let's do the SD so that the numbers are bigger. Same idea, standard deviation. Okay, so for n equals 5, the standard deviation is about 1/4. If I double that, I have now smaller. If I double that again, it's smaller still. So it seems to be decreasing as I increase n, right? And that is expected because of the central limit theorem. What we have is that the standard error should vary with basically 1/√n. So if I increase n, if I take the square root of that number, that's how much the standard error should be decreasing as I'm increasing n, which is exactly what we see here. So this distribution, not only is it becoming more normal, but it's squeezing in more and more and more as I increase the sample size, which is what makes sense, right? Like if you're increasing your sample and estimating the average, it shouldn't matter if you change the sample from one sample to another sample too much, because your sample's so big that your sample average won't change. It's not super sensitive to any data point, because you almost have, it's like if you take the sample average and you have the whole population, that's just a fixed number, right? So if you take the sample average over a slightly smaller than your whole population, it's going to be very, very close every single time to your population average. It's not going to vary a lot. But if you have a very small sample, then with a different sample, you're going to get a very different number. And that's exactly what we're seeing here. So again, that is the idea of the central limit theorem. A little bit of notation. So here, oftentimes for a mean, you'll see mu, because it's m for mean. So maybe you'll see mu denoted used to represent a population mean. And this variance here is I'll call the asymptotic variance of this sample mean estimator. And I'll show you. So I'm just going to move stuff around. So sometimes you see it written like this, and sometimes you see it written like this. So all I've done here is I'll put what we had on the previous slide there. I had that mu. This little squiggly arrow means the distribution of the thing on the left starts to look more like the thing on the right as n increases. Again, the technical details of that, the precise mathematical definition, depends on not just calculus, but really, measure theory, real analysis, stuff that is definitely beyond the pay grade of people here. But you can still understand intuitively by looking at the picture of the sampling distribution, approaching that kind of normal shape. So what I had on the previous slide was that this kind of looks like this. So I had this like sigma star over square root n. That's what I had on the previous slide. So this this distribution here is the same as taking mu plus the normal distribution that's centered at 0 and has a standard deviation of sigma star divided by root n. So what we're saying is that the difference, or the bias between our estimator and the estimand starts to look like a normal distribution centered at 0 and having a standard deviation sigma star over root n. And this thing here, this is the same as a normal random variable, the normal 0, 1 random variable scaled by this scalar. And so I can bring that to the other side too. So here I just would be, I would get this. I would be multiplying by root n and dividing by sigma star. And so this is another way to write that central limit theorem. This is actually the more formal, correct way, because the thing on the right is a fixed thing. It doesn't vary with n. Whereas the way I've written it up here, this thing changes with n. It's kind of like narrowing. Whereas here we're saying this thing approaches some kind of fixed point. We don't have a moving target, but it's understood when I write this that what I mean is this, or vice versa. It's not that important to have the formalism right. The important thing is that you understand the idea, which is the sampling distribution of a sample mean appropriately scaled approaches this normal distribution.